Kia ora koutou. This is a conics question from the 2005 scholarship calculus paper. It's the third part of what I've said before is a pretty hideous question. So I'm just going to quickly show you 6a and 6b in case you haven't looked at them yet. I think hopefully this is here. Yeah, this one is, what's this one? This is 6b. No, this is 6a. Yeah, so this bit is all right. This first bit is fine. And then the second bit that I did about a week ago is this bit here, where we've got a thing getting reflected. I don't know, it doesn't really matter anyway. So, but basically this question is all about a hyperbola. This 6c, I have personally found incredibly difficult to get my head around. But once you see what they're asking for, it's actually not that bad. But it took me a long, long time to see that. So I think this is definitely up there in terms of difficulty. The question goes like this. It's about a completely generic hyperbola. So I've put a picture in here just of an ordinary old hyperbola, but we don't care about any of these points or this reflection stuff, right? We've just got this bit of hyperbola and this bit of hyperbola. And we're told the following thing. Given that the equation of the tangent at a point x1, y1 on the hyperbola is this, we have to find the equation of this tangent in terms of a and b and its gradient m. Okay, so let's just look again with a bad drawing. What it's telling me is that if I go ahead at a particular point and I draw the tangent line in, then it turns out that if I just take my values x1 and y1, I can form my tangent equation this easily. Now, we're not proving why that works, right? We've been given that result. What we're now being asked to do is to find this equation for this tangent line, not in this form where I've got x1 and y1, but just in terms of the a and b from the hyperbola and the gradient of this line, right? So this is going to be useful in a situation where for some reason I know the gradient of a line and I know the equation of the tangent, but I don't know this point. So this question comes down to a whole lot of rearranging. But I don't know why I didn't see that, but I haven't seen that now for 2 years in a row. And I think in exam conditions, this question is problematic. So this is what we're being asked to do. At the moment, buried in here, we've got an equation which is y equals blah, 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 right? We could rearrange this and we'd have y as a function of x1, y1, which is the point on the hyperbola, and a and b. And what we're being asked to do instead is to form that equation of the tangent as a function of x, a, b, and m. Right, so just going over that one more time. When we're given the tangent equation here, it depends on x1, y1, a, and b. And we want to eliminate the x1 and the y1. And so that's one clue about how we should get started. The other thing that we're obviously going to need to do to get anywhere with the gradient is we're going to need to differentiate. And we're going to be differentiating the hyperbola. So I'm going to label a couple of things in here because I'm going to use them again and again. I'm going to call that one star and that one star star. Starting off, what I'm going to do is differentiate this to get dy by dx, and that's going to get me an expression for the gradient. And then I'm going to find the gradient at this particular point, x1, y1. And my goal is going to be to eliminate both the x1 and the y1 in here. So first up, we've got x squared over a squared minus y squared over b squared is equal to 1. When I differentiate it, I get 2x over a squared minus 2y over b squared times dy by dx is equal to 0, and that's using implicit differentiation. If you're not confident with that, go back and find the videos on that topic. Rearranging this should feel pretty easy if you're watching this video by now, because we've done it in lots of other conics questions. So I'm going to get this. I could actually, just to be even clearer, I could leave that negative down in the denominator. So you see what's going on. And now we're going to simplify away the negative 2's, and we're left with b squared x over a squared y, right? So that's the gradient at any point on the curve. Now, just while I'm thinking about it, I'm going to assume in this example that I'm working with a y1 greater than 0, just for the sake of getting through the question a little bit faster. That we'll come to that later on. Right, so what can I say now? Well, we're interested in the tangent at a particular point. So M is at the point x1, y1. So what is it? M is equal to b squared x1 over a squared y1. And we want to end up, remember, with my equation y is equal to blah, 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 and it's going to depend on a, b, and m and x. So I'm now going to start by eliminating x1. Right, so we'll make x1 the subject, and we get x1 is equal to a squared m over b squared times y1. Okay, so that's really useful. What can I do next? Well, think about what we haven't used yet. We've differentiated this hyperbola. So we've said we can find a general expression for the gradient. But I haven't yet used the fact that x1, y1 is special, right? It's a point on the curve. And because it's a point on the curve, it has to satisfy this equation here. So I'm going to substitute in this x1 value into the equation of the curve. So we've got 1 over a squared times x1 squared minus y1 squared over b squared is equal to 1. With a little bit of algebra, we get a to the power of 4. I'm going to do this slowly. So we've got a squared b to the power of 4 here, minus y1 squared over b squared is equal to 1. Cleaning that up gives me a squared m squared y1 squared minus y1 squared over b squared. Whoops, I've lost a b to the power of 4 in there. So all I've done here really is simplify this and this, but not completely. So I'll just, okay, there's my a squared back. Right, now going very slowly, let's get a common denominator. What I'm trying to get here is an expression for y1. So we've got b to the power of 4, and we've got a squared m squared minus b squared, all multiplied by y1 squared equals 1. Right, so all I'm doing here is I've got a common factor sitting in here of y1 squared, but I need to multiply this bit by b squared to get my common denominator. And you can see that we're just about there, right? So now we've got an expression for y1 squared, and it will be b to the power of 4 over a squared m squared minus b squared. Now, as I said before, just to keep this video a bit shorter, I'm going to assume that I'm working with y1 greater than 0, and that means that I know that y1 is equal to b squared over just this. This whole thing works fine. If I have a negative value, then it will be negative down here, right? But let's just work with the positive case for now. Okay, so what do I have? Well, I've got a value for y1, and I've got a value for x1. So let's go back to the start of the question where we had our equation of the tangent to the line. Just clean up this mess. So this line here, this is my tangent, and this is the equation. We've now managed to get both x1 and y1 in terms of a, b, and m. So the last thing left to do is to substitute those into here and then to rearrange. And hopefully we're going to end up with an equation that's in the form y equals mx plus c. There's another way to do this question, but this way I think is probably the easiest way to see it. So we'll start off with just writing that out. X times x1 over a squared minus y times y1 over b squared equals 1 is the tangent equation. We're going to substitute now. And for x1, we've got this pretty straightforward value up here. Right, so we have x over a squared times a squared m over b squared y1 minus y1 over b squared y is equal to 1. Let's just, before we go into a whole lot of big mess, let's look at what we've just figured out here though. We've got y1 is equal to b squared over all of this. And if you look at that, you'll see that in here, we've got a y1 over b squared, and here we've got a y1 over b squared. So you can do a bit of quick work to rewrite y1 over b squared as 1 over this. And that means I can now replace the stuff in green with this. And you can also see that a squared divided by a squared simplifies away. So here now I've got x times m over root a squared m squared minus b squared minus 1 over root a squared m squared minus b squared y is equal to 1. I'm going to multiply everything through by the denominator, and I get mx minus y is equal to this, and rearranging gives me y is equal to mx minus the square root of a squared minus m squared minus b squared. So there you go. A couple of things about this question. First of all, I want to say a big thanks to Nicole Cox for sending me in his lovely working on this problem. And secondly, now that I've done this question, it really doesn't look that bad to me anymore. And I think that's a really common thing that happens when you're doing lots of scholarship practice. I'm sitting here and I'm going, well, what exactly did I find so horrible about that question? Because what we've got now is quite a cool result, that if you know that if you've got a hyperbola here and you can somehow measure this tangent here, you don't have to know this point, right? You can just figure out the gradient of that tangent. And if you know your a squared and b squared for your hyperbola, then you have the exact equation of the tangent to that curve. It turns out that that's going to make part 6D easier than it has to be. Okay. The other way that you could have done this question, in case some of you are wondering, is that you could get down to here, just going back up a bit. So I don't know if anyone's still watching, but suppose we've got down to this result here. So we've got our y1 and we've got our x1. Then instead of substituting into this equation, there is one other way that we could have done this. And that's to say, well, my tangent equation has got to have the form y is equal to mx plus c, right? So what do we know about the plus c? Well, that's my y-intercept. And we've got this equation here. And if you think about how we find the y-intercept, it's by making this 0, right? We just make x or this 0. And that gives me straight away that at x equals 0, we've got y is equal to, what's y equal to? When x is equal to 0, sorry, this whole thing's equal to 1, not 0. Y, negative y times y1 over b squared has to equal 1, which gives me y is equal to negative b squared over y1. And that value y is my y-intercept, right? So in this particular case, here's my tangent equation. And at x equals 0, my y value will be that. So that makes it really easy also for getting to my answer. So y is equal to mx plus c is y equals mx minus b squared over y1. But we know about b squared over y1 because we've figured out what y1 is from above. So remember, y1 was equal to b squared over this. So b squared over y1 is equal to m squared a squared minus b squared. So there are two different ways to do it, but you get quite far through the problem. Whichever way you take, you're going to go quite far through and get your x1 and y1 first. Thanks for watching. I'll be pretty amazed if anyone's made it to 14.5 minutes on this question. If you have, let me know, and there will be a little caramel chocolate bar when you get back to school next week.